Hi everyone, welcome back. Today we're going to be discussing the fundamental theorem of calculus. Now, the fundamental theorem of calculus is broken down into two different parts. The first part that we have here on screen says that if your function f is continuous on an interval from a to b, then the function g defined by g of x, which g of x is defined as the integral from a to x of f of t dt, where x is bounded anywhere between a and b, if that's continuous that is continuous on the interval from a to b, and it's also differentiable on the open interval from a to b. And we also want one more added result here, that g prime of x, in other words, the derivative of g of x, is going to be equal to f of x. So what's going to happen here is that as we start observing this function g of x, we want to take the derivative for g of x, and we want to make sure that we get f of x as a result. Well, I have a depiction here on screen right below the fundamental theorem, and you're going to see the the t and y axis, and I went ahead and relabeled this as f of t. That way we could go ahead and see that x is some variable or some stopping point between the interval from a to b. And if x is able to then be movable between the value of a and b, then that means this area is just going to be produced as a function of x. Now, we know that the area underneath the curve, is represented by a integral. However, in this particular case, we have that area is being modeled by this function g of x. And so as x is either getting smaller or increasing, this area is going to be doing the same. Therefore, we can then model this area by some function. And so that's what the fundamental theorem of part 1 says. Fundamental theorem of calculus part 1 says. Now, we can also have that if we assign the upper limit not as a stopping point x, but instead as a function of the stopping point, then what we can have is we can apply the chain rule in order for this function to still be differentiable. And so here we have that we're going to use the fundamental theorem of calculus part 1 to find these respective derivatives. So using the fundamental theorem of calculus part 1, we're going to go ahead and we're going to find these derivatives. So I'm going to denote here that I'm going to take the differential with respect to x for g of x, but g of x is the function that's made by the integral from 1 to x for cosine of t squared dt. And so we're able to get that the left-hand side of the equation is g prime of x, that's the derivative of g of x. On the right-hand side, what we're going to get to evaluate here is that since we have this function and we're going to be taking the integral, once we take the function and we take this integral, we're going to have to take the derivative with respect to that variable, which will be x. So we could go through the process of what is the antiderivative of cosine of t squared, but then we'd have to go back to finding the derivative with respect to that stopping point. So in a sense, they're going to nullify one another, meaning that they are going to be canceling each other out. So instead of taking the finding the antiderivative and then taking the derivative, what we're going to do is we're going to jump straight to that conclusion, and we're going to say that, hey, we already know what that's going to be. That's just going to be cosine of x squared. The antiderivative, and then we take the function, we wind up right back where we started at, which is the function itself, just evaluated at x, because we took the derivative with respect to x. Now, looking at part B, we're going to do the same thing. We're going to take the derivative of h of x, and we're going to take the derivative with respect to x, and again, as we start looking at this function to take this derivative or to find this antiderivative and then take the derivative, Again, the fundamental theorem of calculus says we don't need to go through the whole process of finding this antiderivative and then taking the derivative because they are inverse operations of one another, which means that h prime of x will then be evaluated for the function at square root of x. So we have the square root of x squared, that's your z squared. We have the square root of x to the fourth, that was your z, plus 1. And we also need to multiply by the derivative of the square root of x. Remember, that's a chain rule. If it doesn't stop at x, and if it stops at some function of x, then we need to go through and we need to make sure that we account for that derivative when we go and, again, apply that derivative. So here, h prime of x, let's see, I want to calculate the derivative here first. So the derivative that I'm going to calculate here first is going to be 1/2 x to the power of negative 1/2. All right, so I'll keep that in my back pocket. Square root of x squared, that's going to just be x. Square root of x to the fourth, that's going to be x squared plus 1, multiplied by that derivative, which we said was 1/2 times the square root of x. And therefore, let's see if we can go through this process here. 1/2 square root of x. We're just going to have x over 2 times the square root of x. And square root of x is going to cancel out with the square root of x up here. So we're left with square root of x divided by 2 times x squared plus 1. And that should be our final answer. So, perfect. Everything's looking good so far. Now, let's look at the last one for part C. Looking at part C, what's going to happen here is that I see that my integral here from, or y is equal to the integral from sine of x to 1, what's going to happen here is that my lower bound is not this constant that we're looking at. So we then have to account for the lower bound not being a constant. In doing so, I'm going to switch the bounds of integration, or the limits of integration, meaning that my integral is going to go from 1 to sine of x, and this is going to be for my function of 1 plus t squared dt. Now I can take the derivative. Taking the derivative of this integral, again, will result in the integral itself. So that's going to be negative 1 plus sine squared of t. And then I'm going to have to multiply by the derivative of sine of x. And again, that's because my upper bound is not a function, is not x itself. It's a function of x. So my derivative here turns out to be negative cosine of x multiplied by the square root of 1 plus sine squared of t. And there we are. That's your final answer. So that's what the fundamental theorem of calculus part 1 is telling us here. Now, the fundamental theorem of calculus part 2. Fundamental theorem of calculus part 2 is then telling us that if f is continuous on an interval from a to b, then the integral from a to b for f of x dx is equal to capital F of b minus capital F of a, where capital F is any antiderivative of the function f. And what we're doing here is we're saying, okay, so we find a function, capital F, such that when we take the derivative of that function, then we get lowercase f of x. Now, we're going to go through the process here, and we're going to start identifying what that means. All right, so using part 1 and part 2 of the fundamental theorem of calculus, we can then arrive at the conclusion that will tell us that if we have an integral from a to b, And if we find a function, as the fundamental theorem of calculus part 2 tells us, where we have the derivative of that function that is being integrated, fundamental theorem of calculus part 1 tells us that if we have an integral and we have an antiderivative, meaning the integral and a derivative, that these are inverse operations of one another, and therefore we only need to evaluate the function at the endpoints and take the difference. That's what the fundamental theorem of calculus tells us. But again, it's broken down into two different parts, part 1 and part 2. But now we want to roll all this into one to start doing these examples. So in this example, it says to evaluate the integral. The integral here is from 0 to 1 for the function 1 minus 8v cubed plus 16v to the 7th dv. So what I need to do here at this point in time is I need to find an antiderivative. So let's go ahead and find that antiderivative. So finding the antiderivative for the integrand here, the antiderivative of 1 with respect to v is just v. The antiderivative of 8v cubed is going to be 2v to the 4th plus the antiderivative for 16v to the 7th is going to be 2v to the 8th. And again, we're evaluating this antiderivative. Now, we don't necessarily need a constant here. Typically, when we want the antiderivatives, we request a constant. And that's because we want any antiderivative of that form. However, in this instance, we're evaluating that function between 0 to 1. So when we look at the antiderivative, we're still going to evaluate that antiderivative from 0 to 1, which implies that we don't need to know what the constant is. So then, all we're going to do is evaluate this from 0 to 1. Now notice the notation that I'm using here. The notation that I'm using here is this vertical line. Lower bound of the lower line is 0, upper bound is 1. Those are the same bounds that we use for the integral. When we evaluate this, I need to evaluate my function at 1. And then I need to evaluate my function at 0 while subtracting that function that I'm evaluating at 0. And again, that's by fundamental theorem of calculus part 2. So here you're going to see everything, or all of the terms on that last function evaluated at 0 are going to cancel out. So they all in themselves cancel out. They're all going to go to 0. And we're really only left with 1 minus 2 plus 2, where this just evaluates to just be 1. And that's how we want to approach these specific integrals. So let's work on part B really quickly, and let's see where part B leads us into. So part B, we want to evaluate the integral from 0 to 4, and this is going to be for the function 4 minus t times the square root of t dt. So again, we would just want to find the antiderivatives. And some antiderivatives might be a little bit harder to find than others, but we got to stick with the algebraic manipulations that we know, or the algebraic simplifications that we've been accustomed to, as well as the trigonometric antidifferentiation that we've learned. So here, what I want to do is I need to evaluate this antiderivative. So what I'm going to do is I'm going to distribute the square root of t into that binomial. By doing so, I'm going to treat the square root of t as t to the power of 1/2. And so when I distribute, I'm going to be left with 4 times t to the power of 1/2 minus t has an exponent of 1, but when it multiplies t to the power of 1/2, the exponents are going to add, which means we're going to be left with t to the power of 3/2, and this is going to be dt. As we find the antiderivative now, because now this function is in the perfect form to find the antiderivative. So finding the antiderivative for 4 t to the power of 1/2, what we're going to do is we're going to add 1 to the exponent. So t to the power of 1/2 plus 1, that's then going to get us t to the power of 3/2. And then we multiply by that reciprocal. So multiplying by the reciprocal of that function, we're going to multiply by 2/3, and we're going to multiply 4 by that 2/3, which should get us 8/3. Because again, we have that constant of 4. Minus t, again 3/2, we're going to add 1 to that exponent. Adding 1 to the exponent should get us 5/2. And then we multiply by that reciprocal, which is 2/5. Again, I don't need a constant for this antiderivative because I'm evaluating from 0 to 4. And I'll just denote it here with that vertical bar. And it's mandatory that we must put that because we must show that we are evaluating the antiderivative from 0 to 1. In doing so, we take 8/3 t to the power of 3/2, where t is 1, minus 2/5 times 1 to the power of 5/2, minus, same function, evaluated at 0, and there we are. Now again, we get to see that the last two terms, they initially or will cancel out because they're evaluated at 0, so they just turn into a constant of 0. And what we're left with is going to be 8/3 minus 2/5. And so as we go through this calculation for 8/3 minus 2/5, I'm going to convert them into the same denominator. So I want both of them to have a denominator of 15. So I'm going to multiply 5 times 8, and that's going to be 40. I'm going to multiply, oh, sorry, not 40. Oh, yes, sorry, 40. Cheese and crackers. 40 over 15, there we are, minus the 2, I'm going to multiply by a 3, so that's going to be 6 over 15. Now, I realize I made a mistake. Oh my goodness. This is why I like doing these in class. The values were from 4 to 0, not from 1 to 0. So the values were from 4 to 0. There we are. I'm making those changes here really quickly. There we are. So let's make those changes before we carry on any further. Okay, so slight change in plans. So what I'm going to do is I'm going to evaluate 4 to the power of 3/2 really quick. So I'm going to do 4 to the power of 3/2 over here. 4 to the power of 3/2 is the square root of 4 to the power of 3. And again, square root, that's because we have a half on the exponent. Square root of 4, that's 2, so it's going to be 2 cubed, which is 8. So 4 to the power of 3/2 is really just 8. So 8 times 8 should get us 64 over 3. Minus, we're going to do same process here. Square root of 4, that's going to be 2. 2 to the 5th, that's going to be 32. 32 times 2, that's going to be 64 divided by 5. There we are. Now I want the same denominator. So I'm going to take 64 and I'm going to multiply that by 5. I should get 320 over 15 minus, I'm going to take 64 and multiply by 3. It's going to be 192 over 15. And so now all I have to do is 320 minus 192, which should get me 128 over 15. And there's the final answer. Perfect. So again, minor mistake on my end. My apologies for that, but as long as we correct it, we're on the right track. So now that we got part B down, let's look at part C. Part C, we want to evaluate the integral from -1 to 2 for 3u minus 2 times u plus 1 du. And again, the differentials here let us know with respect to what variable we're going to be integrating with. So the thing about this antiderivative is we cannot integrate a product of antiderivatives yet. We can do it at a later time, but we need more tools at our disposal to do that. Now, in order to do it at this point in time, what we have to do is we have to get this integrand into a form that we know how to integrate, which means it's either a polynomial or exponential or not rational, but rational exponents, something of that form. So what I want to do is distribute 3u times u, that's 3u squared, 3u minus 2u, that's going to be u. Negative 2 times 1 is negative 2. This is all du. Now we can integrate term by term. The antiderivative for 3u squared will be u to the power of 3. The antiderivative for u, we add 1 to the exponent, and then we multiply by the reciprocal, minus 2 times the antiderivative of 2 is just u, because that's the variable that we're doing this with respect to. And then we evaluate from -2 to 1. So taking the first evaluation here, that's going to be 2 to the power of 3 plus 1/2 times 2 to the power of 2 minus 2 times 2. And then I'm going to subtract out the function evaluated at -1. -1 cubed plus 1/2 times -1 squared minus 2 times -1. Notice in this particular instance, very different to the previous examples, the function evaluated at the last endpoint, which is -1, isn't canceling out. So we still have to go through the calculation to evaluate this. 2 cubed, that's 8. 1/2 times 4, that's going to be 2, minus 2 times 2, that's 4. -1 cubed, that's -1, but distribute the negative, and that becomes a plus 1. -1 squared, that's positive 1 multiplied by 1/2, so that's positive 1/2. Distribute the negative, that's -1/2. -2 times -1, that's positive 2, but then distribute the negative, that now gets us -2. So we can go through and combine our like terms. We have 2 minus 2, so these will simplify out, they'll cancel. Then we have 8 minus 4, that's going to be 4 plus 1, that's 5. So we get 5 minus 1/2. But 5 minus 1/2, let's see, multiply that by 2, that's 10. That should get me 9/2. There we are. So the integral evaluated from -1 to 2 for the function that has 3u minus 2 quantity multiplied by u plus 1 will then evaluate to just be 9/2. Awesome. Very good so far. Let's look at part D. For part D, I want the integral from -pi4 to pi3, and I want to evaluate this for the function of cosecant squared theta d theta. So what we have to do here is we then have to find the antiderivative. We have to go through and we have to find the antiderivative for cosecant squared theta. And so what you want to do is you want to go into your techniques of integration and you want to find out your techniques of differentiation, and you want to find out what function did we take the derivative initially for in order for us to get cosecant squared. Well, we initially had to take the derivative of cotangent to get negative cosecant squared. All right, so I'm going to write that on the right-hand side. I'm going to say note the derivative of cotangent of x is negative cosecant squared of x. And so since we have cosecant squared of theta here without the negative, we know that if we have to take the antiderivative, then the antiderivative is going to have to account for the negative value. So that's exactly what we'll do. Account for the negative, but then we had to take the derivative for cotangent in order to get cosecant squared. So this must be negative cotangent of theta that we're evaluating here. And this is going to be evaluated from negative pi fourths to pi thirds. So the evaluation then becomes negative cotangent at pi thirds minus negative cotangent at pi fourths. Awesome. So at this point in time, we then need to evaluate what is cotangent at pi thirds. So here we have cotangent at pi thirds. Now cotangent at pi thirds, cotangent is the ratio for cosine over sine. So we're going to be looking for the value of cosine at pi thirds, and we're going to be dividing that by the value of sine at pi thirds. So the value of cosine at pi thirds is 60 degrees. So when we look at the value of 60 degrees, we're going to look at the cosine argument, and the cosine is going to be 1/2 at pi thirds. The sine argument of pi thirds, or the sine evaluated at pi thirds, is going to be √3/2. So there's my cotangent. Negative and negative for cotangent of pi fourths. Nice part about cotangent of pi fourths is that tangent of pi fourths is just 1, because that's √2/2, divided by √2/2. And cotangent is just the reciprocal of that evaluation, which is just 1, so it's still just 1. So that's going to be negative times a negative, that's positive 1. Now, for the previous one that we evaluated, cotangent, notice that the halves are going to cancel, and we're going to be left with negative 1 over √3 plus 1. And this will then simplify. Let's see if we can simplify this just a little bit more. Negative √3 over 3 plus 1. And I'm going to leave it as such. Negative √3 over 3 plus 1. There we are. That's our final answer. So everything looks pretty good so far. Now, let's look at one more, let's say, problem. Let's say that we were given a problem like this, where we want to sketch the region enclosed by the curves y is equal to 2x minus x squared and y is equal to 0, and find its area. All right, so our job here is to sketch the region that's enclosed by these curves. the nice part about one of these curves, I'll say this curve here, is that this is just the x-axis. Y is equal to 0 is a horizontal line at y is equal to 0. In other words, it's the x-axis that we know. The only real, let's say, issue that we're going to have is to graph this parabola. So in order to graph this parabola, we need to know what's the vertex. More than what's the vertex, we also need to know the x-intercepts, because the x-intercepts are going to cross the x-axis, which means they're going to cross y is equal to 0. So what I'm going to do here to find the vertex of this parabola, instead of completing the square and getting this into vertex form, what I'm going to do is I'm just going to use my vertex formula. The vertex formula that I'm going to be using lets me know that I can identify a vertex as long as I know what b and a are within my function, and then take the function and evaluate it at b over 2a. As soon as we do that, we found the vertex. So identifying what's my a and what's my b value is 2, my a value is -1. So as I'm finding my vertex, let's see, b, that's 2, divided by 2 times -1, but that's negative. Negative times a negative is positive. 2 divided by 2 is going to be 1, so this is going to be just 1. Take this number and plug it into your parabola. 2 times 1 minus 1. 2 times 1 minus 1 should get us just 1. There's our vertex. X-intercepts. So in order to find the x-intercepts, we got to set y is equal to 0. And so to do this, we're going to have 0 is equal to 2x minus x squared, which means 0, factor out the x, is equal to x times 2 minus x, which means that x is equal to 0, or x is equal to 2. There's our x-intercepts. We got 0, 0, and we got 2, 0. Let's graph this, now that we got everything that we need. Okay, I think this is all in the first quadrant, so that looks pretty promising. Alright, so here we are. Alright, so I know that I have my x-axis here, which is y is equal to 0. Alright, so there we are, that's y is equal to 0. And now I need my parabola. We know that the vertex was at 1, 1, that's what we found. And then the intercepts were at 0, 0, and at 2, 0. Which means this parabola looks like this. The area that's bounded by these two curves is the area right in here. In other words, we want to find that area. So as we go through and we want to find that area, we know that setting up the integral to find that area, well, we need some integral bounds. So my x values, because we're going to integrate the top portion here, the top of that function is 2x minus x squared. So we know it's 2x minus x squared that we're integrating. Now the x values, the area for the bounds, those x bounds go from x is equal to 0 to x is equal to 2. So we integrate from 0 to 2. All we have to do is find this integral. Antiderivative for 2x should just be x squared. antiderivative for x squared, add 1 to the exponent, multiply by the reciprocal, evaluate this from 0 to 2. 2 squared minus 1/3 times 2 cubed. Subtract out the function evaluated at 0. Again, we don't worry about the last terms because they're all evaluated at 0. There's no constants. They all cancel out. Which means we're going to be left with 2 squared, which is 4, minus 2 cubed, that's 8, divided by 3. 3 times 4, that's going to get us 12. 12 minus 8, that's going to get us 4, so we get 4/3. There's the area. The area here represented in blue that's bounded between those two curves is the value of 4/3. Now, we could say 4/3 square units, or units squared. So we'll just say square units. Because whatever the units are, whether they be centimeters, inches, yards, acres, whatever it may be, it's going to be squared because this is an area. And we're going to be discussing more of this type of topic as we continue through the sections. So I thank you all for joining me on this lesson, and I hope you enjoyed it. And stick around, and we're going to be talking about indefinite integrals and the net change theorem next.